Here's a question that keeps people awake at night. Why is it that when you were 12 years old, you could run around all day, fall down, get up, keep going, and feel perfectly fine? But now, maybe you're 40, 50, 60. You sit in a chair too long and you're tired. You walk up a flight of stairs, you need a break. What happened? Where did your energy go? Now you might think, well, that's just getting old. Everybody knows that. But see, that's not an answer. That's just a label. A physicist doesn't want labels. A physicist wants to know the mechanism, what's actually happening inside your body at the level of atoms and molecules that makes you feel this way. And here's where it gets unsettling, because the answer isn't what you'd expect. It's not simply that you're running out of fuel. It's not that your batteries are dying. The truth is much stranger. And it has everything to do with the most fundamental laws of physics, the same laws that govern stars and engines and the entire universe. So let me tell you what we're going to figure out together. By the end of this, you're going to understand exactly what energy means in a living body. You're going to see why the second law of thermodynamics, this ancient law that rules everything, has a very personal stake in your life. And you're going to understand why, from the point of view of physics, aging isn't just inevitable. It's written into the fabric of reality itself. Now wait, before we dive in, I want to clear something up. When I say energy, I mean something very specific. In physics, energy is the capacity to do work. That's the definition. It's not some mystical life force. It's not chi or prana or whatever else people want to call it. Energy is a measurable quantity, measured in joules or calories, and it follows precise mathematical laws. When you feel energetic, that's not just a feeling. It corresponds to real, measurable physical processes in your cells. And when you feel tired, that also corresponds to real physical changes. The chemistry of your body is different. The rate of certain reactions has changed. This is science, not poetry. And that's what makes this so interesting. Because once you understand the physics, you can actually do something about it. Not everything, of course. Some things are beyond your control. But understanding the mechanism is the first step to influence. But let's start somewhere simple. Let's start with breakfast. You had some eggs this morning, maybe some toast, a cup of coffee. Now, what happens to that food? Most people would say, well, it gives me energy. And that's true, but it's very vague. What does that even mean? Let's be precise. When you eat that piece of toast, your body breaks it down. The carbohydrates in there, they get split apart into glucose, simple sugar molecules. Now those glucose molecules enter your cells. And inside your cells, there are these remarkable little structures called mitochondria. Tiny little things, about the size of bacteria. In fact, we think they used to be bacteria billions of years ago. They got swallowed up by larger cells and decided to stay, to cooperate. A very ancient partnership. These mitochondria, they're your power plants. They take that glucose, and through a series of chemical reactions, they extract energy from it. But here's the thing. They don't just release energy in a big burst like a fire. No, they're much more clever than that. What they do is they capture that energy and store it in a special molecule called ATP, adenosine triphosphate. Now this is a wonderful little gadget. It has 3 phosphate groups attached to it, and those phosphate groups are held together by what we call high energy bonds. It's like a compressed spring. The energy is stored in that tension, ready to be released. And here's what's astonishing. Your body, right now, sitting there, is making and using about 50 kilograms of ATP every single day. 50 kilograms! That's more than your body weight. How is that possible? Well, because each ATP molecule gets used and recycled thousands of times. It's like having a rechargeable battery that gets plugged in over and over again throughout the day. Let me give you a sense of scale here, because this is remarkable. At any given moment, you have only about 50 grams of ATP in your entire body. Just 50 grams. yet you turn over 50 kilograms in a day. That means each molecule is recycled about 1,000 times per day, once or twice per minute, every minute, around the clock. A single cell, and you have trillions of them, consumes about 10 million ATP molecules per second. 10 million per second. Just one cell. The numbers are staggering. And it all happens without you thinking about it, without you knowing about it. This immense chemical factory is operating inside you right now. Every single thing you do requires ATP. Your heart beating, that's ATP. Your brain thinking, ATP. Your muscles moving, ATP. Even just sitting still, your cells are constantly busy, using ATP to maintain themselves, to keep everything organized, to pump things in and out. Your brain alone uses about 20% of your total energy. A fifth of everything you eat goes to powering that 3-pound lump of fat and protein in your head. It's constantly firing neurons, maintaining ion gradients, synthesizing neurotransmitters. It never rests, even when you're asleep. In fact, certain brain activities actually increase during sleep. So when you say you feel tired, what's really happening is that somewhere in this chain, from food to mitochondria to ATP to action, something isn't working as well as it used to. Now let's talk about what happens as we get older. And this is where it gets interesting. Your mitochondria, these little power plants, they're not perfect. In fact, they're kind of messy. When they're converting glucose into ATP, they're also producing something else. Byproducts, these things called reactive oxygen species, free radicals. You've probably heard of them. Think of it like a car engine. The engine burns fuel and produces power, but it also produces exhaust, pollutants, waste, heat. Your mitochondria are doing the same thing. They're not 100% efficient. Nobody is. No machine is. This is a fundamental consequence of the laws of thermodynamics, and there's no escaping it. Let me be more precise about this. In thermodynamics, we talk about the efficiency of an engine. A perfect engine, a theoretical ideal called a Carnot engine, would convert heat into work with no losses. But a Carnot engine would have to work infinitely slowly. It's an ideal that can never be achieved in reality. Real engines, including biological ones, have efficiencies that are significantly less than the theoretical maximum. Your mitochondria are actually remarkably good, about 40% efficient at capturing energy from food. That's better than most car engines, but it still means 60% of the energy is lost as heat. This is why you're warm. You're constantly radiating waste heat from your metabolism. And along with that heat, you're producing chemical waste, those free radicals. Now here's the problem. Those free radicals, those reactive oxygen species, they're chemically aggressive. They bounce around inside your cells, and they damage things. They damage proteins. They damage the membranes of cells, and most importantly, they damage DNA, including the DNA inside the mitochondria themselves. Now this is key. Your mitochondria have their own DNA. It's separate from the DNA in your cell nucleus. This is a remnant of their bacterial ancestry. They brought their own genetic material with them billions of years ago, and they've kept it ever since. This mitochondrial DNA is more vulnerable to damage than nuclear DNA for several reasons. First, it's right there in the mitochondrion, very close to where the free radicals are being produced. It's like living next to a factory that's constantly spewing pollutants. Second, mitochondrial DNA doesn't have the protective proteins called histones that nuclear DNA has. It's more exposed. Third, the repair mechanisms for mitochondrial DNA are less sophisticated than those for nuclear DNA. So you have this tragic situation. Your power plants are producing the energy you need to live, but in doing so, they're slowly damaging themselves. It's like an engine that gradually corrodes from its own exhaust. And over time, decades of time, this damage accumulates. The mitochondria don't work as well. They produce less ATP. They actually produce more free radicals as they get damaged, which creates a vicious cycle. Less energy, more damage, less energy. And you feel it. You feel it as that general sense of fatigue, that difficulty recovering from exercise, that need for more sleep, that sense that you just don't have the get up and go you used to have. But wait, let me back up. because I want you to understand this from a deeper level. I want you to see the physics underneath all of this biology. There's a physicist named Erwin Schrödinger. You might have heard of him. He's famous for his cat. But he also wrote a little book called What is Life? It was published in the early 1940s, and it was extraordinary because it asked a very simple question. What makes living things different from non-living things? What's special about life? Now, Schrödinger was a quantum physicist. He invented the wave equation that describes how particles behave. So he knew a thing or two about fundamental physics. And he looked at biology, and he thought, this is strange. Living things seem to violate the laws of physics. They maintain order in a universe that tends toward disorder. And Schrödinger, thinking like a physicist, came up with a beautiful answer. He said that living organisms maintain themselves by feeding on what he called negative entropy. Now that sounds strange. What does entropy have to do with eating breakfast? Let me explain. Entropy is a concept from thermodynamics. It was invented by a German physicist named Rudolf Clausius in the 1860s. It's often described as disorder, but that's not quite right. It's more accurate to say entropy is a measure of how spread out and dispersed the energy in a system is. Low entropy means energy is concentrated, organized, available to do work. High entropy means energy is spread out, disorganized, degraded into heat. Let me give you a concrete example. Imagine you have a cup of hot coffee and a room full of cold air. The coffee has low entropy relative to the air. The heat is concentrated in one place. Now, if you leave the coffee sitting there, what happens? It cools down. The heat flows from the coffee into the air. After a while, everything is at the same temperature. The energy is spread out evenly. The entropy has increased. This process is irreversible. You never see a cup of coffee spontaneously getting hotter while the air around it gets colder. That would be a decrease in entropy, and it doesn't happen. This is the second law of thermodynamics. The second law of thermodynamics says that in any isolated system, entropy tends to increase over time. Things fall apart. Hot coffee cools down. Mountains erode. Castles crumble. Order gives way to disorder. This is the arrow of time. By the way, this is the only law in physics that distinguishes the past from the future. All the other laws, Newton's laws, Maxwell's equations, even quantum mechanics, they work the same forwards and backwards in time. But the second law gives time a direction. Entropy was lower in the past and will be higher in the future. That's why we remember the past but not the future. That's why causes come before effects. The arrow of time is the arrow of entropy. So how do living things maintain their organization? How does your body, with all its intricate structures, all its precisely arranged molecules, stay organized year after year? Because left to themselves, things should fall apart. Schrödinger's answer was that living things are not isolated systems. They're open systems. They take in low entropy energy from the environment in the form of food and sunlight, and they export high entropy waste in the form of heat and waste products. They maintain their own order by increasing disorder elsewhere. When you eat that piece of toast, you're not just taking in energy, you're taking in organized energy. The chemical bonds in those carbohydrate molecules represent order, structure. Your body breaks down that structure, captures some of the energy, and releases the rest as heat. The total entropy of the universe increases, as it must. But locally, inside your body, you maintain your low entropy state. You stay organized. This is what life does. Life is a process of taking in order and exporting disorder. It's like swimming upstream in a river that's constantly flowing toward chaos. Now here's the unsettling part. As you get older, this process becomes less efficient. Think about it this way. Every time your mitochondria make ATP, they're performing an energy conversion. And no energy conversion is perfect. Some energy is always lost as heat. Some order is always degraded into disorder. The second law demands it. In a young, healthy cell, the machinery is in good shape. The energy conversion is reasonably efficient. The damage is repaired quickly. The system runs smoothly. But as time goes on, damage accumulates. The mitochondria become leaky, they don't capture energy as efficiently, they lose more to heat, they produce more damaging byproducts. The repair systems themselves get damaged and don't work as well. So more and more of your food energy just goes to heat. Instead of useful work, you have to eat the same amount or even more, but you get less usable energy out of it. It's like trying to run a power plant with worn-out, inefficient turbines. Now, I want to make sure you really understand this. So let me give you a different way to think about it. Imagine you have a bucket with water in it, and you want to use that water to turn a water wheel. If the bucket is high up and the water can fall a long way, you get a lot of useful work out of it. But if the bucket is low, the water doesn't have far to fall, and you don't get much work. The food you eat is like water in a high bucket. It has potential. It can do work. Your mitochondria are like the water wheel, capturing that potential and converting it to useful motion. But here's the thing. In thermodynamics, we talk about free energy. That's the energy that's actually available to do work. Not all the energy in your food is free energy. Some of it is bound up in ways that can't be extracted. This is subtle, so let me be careful. The total energy in a system is conserved. First law of thermodynamics. Energy cannot be created or destroyed. But not all energy is equally useful. Some energy is high quality, concentrated, available to do work. Some energy is low quality, dispersed, unavailable. When you burn a piece of wood, the total energy is conserved. The chemical energy in the wood becomes heat energy in the flames and warm air. Same total amount, but the quality has changed. The chemical energy in the wood was high quality, available to do work. The dispersed heat in the room is low quality, much less available to do work. This is the connection between energy and entropy. High quality energy has low entropy. Low quality energy has high entropy. Every time energy is converted from one form to another, some of it degrades. Some useful energy becomes less useful. The total stays the same, but the quality declines. As your mitochondria get damaged with age, they become less able to capture the free energy in your food. It's like the water wheel getting rusty and stiff. The water is still falling, but the wheel doesn't turn as well. More energy is lost to friction, to heat, to inefficiency. Let me give you some numbers to make this concrete. A gram of glucose contains about 4 kilocalories of energy. In an ideal, perfectly efficient process, your mitochondria could convert all of that into ATP. But in reality, they capture only about 40%. The rest becomes heat. Now, 40% might not sound great, but actually it's remarkable. Car engines are typically only about 25% efficient. Power plants are maybe 30 to 40%. Your mitochondria are doing pretty well for a biological system. But here's the thing. As mitochondria age and accumulate damage, that efficiency drops. Maybe it goes from 40% to 35%, then to 30%. The absolute numbers might not sound like much, but over the course of a day, processing all that ATP, it adds up. And it's not just efficiency. Damaged mitochondria also have trouble responding to increased demand. When you're young and you start exercising, your mitochondria can ramp up ATP production quickly. The proteins in the electron transport chain are in good shape, the membranes are intact, everything works smoothly. When you're older, the response is slower. The mitochondria can't ramp up as fast. They're more likely to stall, to produce reactive oxygen species instead of ATP. This is why you might feel okay at rest but struggle when you try to do something demanding. Your baseline power is still there, but your peak capacity is reduced. This is why, even if you eat the same amount as when you were young, you might gain weight. Your body isn't converting food to useful energy as efficiently. More of it ends up stored as fat or lost as heat. Now let me tell you something even more remarkable. Something that researchers have measured. When you're a baby, in your first year of life, your metabolic rate, adjusted for body size, is enormously high, about 50% higher than an adult. You're a little furnace, burning through energy at a tremendous rate. That's because you're growing, building new tissues, developing your brain. By the way, the human brain is the most expensive organ to build. A baby's brain uses about 60% of its total energy. 60%! That's why babies sleep so much. Their brains are doing enormous amounts of construction and wiring while they sleep. It's like having a major renovation project going on around the clock. Then, throughout childhood and adolescence, your metabolic rate gradually declines. By the time you're about 20 years old, it levels off. And here's the surprising part. It stays roughly constant, adjusted for body size, from your 20s all the way to about 60 years old. That's right. Your metabolism doesn't really slow down significantly in your 30s or 40s or 50s. All those people who say their metabolism crashed in their 30s, they're wrong. Well, not completely wrong. Their total energy use probably did go down, but not because their cells became less efficient. It's because they became less active. They lost muscle mass. They sat more. They exercised less. This was shown in a big study published a few years back. Researchers looked at over 6,000 people from 29 countries, ranging in age from 8 days old to 95 years. They used a technique called doubly labeled water to precisely measure how many calories these people were burning, and they found this surprising result. From 20 to 60, adjusted for body size and composition, metabolic rate is essentially flat. Now, unadjusted metabolic rate does decline during this period, but that's because people tend to lose muscle and gain fat. Muscle is metabolically expensive tissue. It burns calories just sitting there. Fat is cheap to maintain. So, as your body composition shifts, your total energy needs decline. But that's not your cells becoming less efficient. That's you losing muscle. This is an important distinction. If you maintain your muscle mass, you can maintain your metabolic rate well into middle age. Exercise, particularly resistance training, is absolutely key here. But after 60, something changes. From 60 onward, there's a genuine decline, about 0.7% per year. By the time you're 90, your metabolic rate is about 25 to 30% lower than it was in middle age. And this isn't just from losing muscle or becoming less active. Even accounting for those things, there's a real decline in how efficiently your cells burn energy. This is the damage I was talking about, the accumulated wear and tear on your mitochondria, the buildup of errors and inefficiencies, the gradual degradation that the second law predicts. Now wait, I said something important, and I want to go back to it. I said that the second law predicts this. Let me be careful here, because this is profound. The second law of thermodynamics isn't a suggestion. It's not something that might happen. It's something that must happen. In any system that's doing real work, that's converting energy, entropy must increase, damage must accumulate, efficiency must decline. There's no way around it. Some physicists have even calculated what they call lifespan entropy, the total amount of entropy your body produces over your entire life. And remarkably, this number seems to be roughly constant across individuals. About 11,000 kilojoules per degree, Kelvin per kilogram of body mass. Now let me explain what that number means. It's a measure of how much thermodynamic irreversibility your body has gone through, how much order you've converted to disorder, how much free energy you've degraded into heat. Think of it like a budget. You're born with the ability to process a certain amount of entropy, to maintain your low entropy state for a certain amount of thermodynamic work. And when you've used up that budget, the game is over. Different species have different budgets, scaled roughly by body mass. But within a species, the number is surprisingly constant. It's as if there's a fundamental limit to how much thermodynamic processing a given amount of tissue can do before it breaks down. Now, that's a strange way to measure a life, isn't it? In units of entropy. But it tells you something deep. It suggests that there's a kind of thermodynamic budget to living. You're born with the ability to generate so much entropy, to process so much order into disorder, and when you've used up that budget, you're done. This connects to something called the rate of living theory, which I mentioned earlier. The idea that metabolic rate and lifespan are inversely related. Burn fast, die young. Burn slow, live long. It's not the whole story, but there's something to it. Here's what I find fascinating. A hummingbird and an elephant both process roughly the same amount of entropy per kilogram of body mass over their lifetimes. The hummingbird does it in a few years, metabolizing frantically to power its tiny wings, beating 80 times per second. The elephant does it over 60 years, plodding along at a more leisurely pace. Same thermodynamic journey, different speeds. But let's be careful. Let's not get too fatalistic here. Because the second law doesn't say how fast entropy has to increase. It just says it has to increase. And here's where things get interesting from a practical standpoint. There are certain things that speed up the entropy production in your body. One is overeating. When you take in more energy than you need, your mitochondria have to process it all, and that produces more waste, more damage. Another is inactivity. Paradoxically, not using your mitochondria makes them weaker. They atrophy. They become less efficient. And there are things that slow it down. Moderate caloric restriction, eating a bit less than you might want, has been shown in many organisms to extend lifespan and preserve mitochondrial function. Exercise, while it temporarily increases energy use, actually makes your mitochondria stronger and more efficient in the long run. Like training any system, working it makes it better. Sleep matters too. During sleep, your body repairs a lot of the damage that accumulated during the day. It's like scheduled maintenance for a power plant. If you don't get enough sleep, the damage builds up faster. Let me give you another thought experiment. Imagine two identical twins at birth. Same genes, same mitochondria, same everything. But one of them lives a very active life, exercises regularly, eats moderately, sleeps well. The other is sedentary, overeats, sleeps poorly. By the time they're 60, they'll be very different. The active twin will have mitochondria that are still functioning well, producing ATP efficiently, generating fewer damaging byproducts. The sedentary twin will have mitochondria that are struggling, inefficient, creating more damage. The second law applies to both of them equally, but the rate at which they're approaching thermodynamic equilibrium, approaching death, is quite different. The active twin has found ways to slow down the inevitable, to swim upstream more efficiently. Now, I want to address a common misconception. People often think that feeling tired means they don't have enough energy. They think, I just need more fuel, more food, more coffee, more sugar. But that's not usually the problem. The problem isn't lack of fuel. The problem is the inability to efficiently convert fuel into useful work. Think about it. An obese person has enormous energy stores. Fat is packed with energy, but they often feel tired. Why? Because their metabolic machinery isn't working efficiently. Their mitochondria are stressed. Their cells are having trouble processing all that fuel. It's like having a room full of wood but a fireplace that's clogged with soot. You don't need more wood. You need to clean the fireplace. This is why exercise helps fatigue, even though it uses energy. Exercise improves mitochondrial function. It triggers your cells to produce more mitochondria and to clear out the damaged ones. It's like tuning up your engines. Let me explain this more carefully because it's counterintuitive. You would think that exercise, which uses energy, would make you more tired. And in the short term, it does. Right after a workout, you're fatigued. But over time, regular exercise makes you less tired overall. Your baseline energy level goes up. Here's why. When you exercise, you're stressing your mitochondria. You're demanding more ATP than usual. This stress, if it's not too extreme, triggers adaptive responses in your cells. They think, we need more power plants, and they respond by building more mitochondria. This is called mitochondrial biogenesis. But they also do something else. They get rid of the damaged, inefficient mitochondria. Because under stress, you can't afford to carry dead weight. You need your energy systems working well. Let me tell you about something called mitophagy. That's a process where your cells actually destroy their own damaged mitochondria and recycle the parts. It's a quality control mechanism. When a mitochondrion gets too damaged to work properly, the cell tags it for destruction and breaks it down. The word mitophagy comes from the Greek words for mitochondrion and eating. The cell is literally eating its own mitochondria. It sounds violent, but it's actually a crucial maintenance process. In young cells, this process works well. Damaged mitochondria are efficiently removed, and new healthy ones are produced to replace them. But as we age, mitophagy becomes less efficient. Damaged mitochondria accumulate. They don't get cleared out. They sit there, leaking free radicals, producing less ATP, clogging up the works. This is one of the key differences between young and old cells. Young cells are good at taking out the garbage. Old cells let the garbage pile up. Exercise stimulates mitophagy. It's like telling your cells, hey, we need good power plants here, get rid of the bad ones. Fasting, intermittent fasting, also stimulates mitophagy. When food is scarce, your cells become very efficient at recycling their damaged components. There's a molecule called AMPK that acts as a fuel gauge for your cells. When energy is low, AMPK gets activated, and it triggers all sorts of cleanup and repair processes, including mitophagy. Exercise activates AMPK, fasting activates AMPK, caloric restriction activates AMPK. This might explain why moderate stress seems to be good for longevity. Not severe stress, that's destructive. But mild stress, what researchers call hormesis, seems to trigger adaptive responses that make cells stronger and more resilient. Now here's something beautiful from a physics standpoint. Your body isn't just a machine that takes in fuel and produces work. It's a machine that maintains and repairs itself. It's a self-renewing system. In fact, most of the atoms in your body right now weren't there 7 years ago. They've all been replaced. You're constantly breaking down old molecules and building new ones. Your proteins, your membranes, even the minerals in your bones. Everything turns over. So why do you age at all? If you're constantly rebuilding yourself, why don't you just rebuild perfectly and stay young forever? The answer goes back to the second law. Those repair and rebuilding processes themselves require energy. They involve copying information, following molecular blueprints. And every time you copy something, there's a chance for errors. Every time you do work, there's waste and damage. It's like trying to maintain a building by constantly replacing bricks. If your brick-making factory is slightly damaged, the new bricks won't be quite as good as the old ones. And over time, the building gradually degrades, even though you're constantly repairing it. Your DNA is like the blueprint for your cells, but it accumulates mutations over time. Your proteins are folded into precise shapes, but they accumulate misfoldings. Your mitochondria have their own DNA, and it accumulates damage even faster than nuclear DNA because it's right there next to all those free radicals being produced. Let me explain what I mean by information degrading. Your DNA is a code. It's written in a 4-letter alphabet, the bases A, T, G, and C. This code specifies how to build every protein in your body. It's an instruction manual for making you. When a cell divides, it has to copy all of this DNA, and the copying process is remarkable. The enzymes that do the copying are incredibly accurate. They make only about 1 mistake in every billion bases. That's like copying out the Encyclopedia Britannica 1,000 times and making only 1 typo. But 1 in a billion isn't 0, and you have trillions of cells, and they're dividing all the time. So mistakes accumulate, mutations. Most of them are harmless. Some are caught and repaired, but a few slip through. And then there's damage from external sources, radiation, chemicals, those free radicals we talked about. Your DNA is constantly being damaged and repaired. Usually the repair works, but sometimes it doesn't. Sometimes the damage is fixed incorrectly. Sometimes it's not fixed at all. Over decades, this adds up. The blueprint gets smudged, the instructions become harder to read, the proteins that get made aren't quite right, they don't fold properly, they don't function as well. And here's the cruel part. The repair machinery itself is made of proteins that are built from the degraded blueprints. So the repair machinery becomes less efficient over time. It's a downward spiral. The worse the blueprint, the worse the repair. The worse the repair, the worse the blueprint. Information degrades. That's entropy at the level of data. And as information degrades, the structures built from that information become less precise, less functional. This is related to something deep in physics called the connection between information and entropy. There's a physicist named Rolf Landauer who showed in the 1960s that erasing information has a thermodynamic cost. It produces heat. Information is physical. Your cells are constantly processing information, reading DNA, building proteins, sending signals, and every time information is processed, there's a chance for error. Every time it's copied, there's potential for degradation. This is unavoidable. It follows from the same laws that govern computer memory and communication systems. This is the deep tragedy of living systems. The very process that keeps you alive, metabolism, energy conversion, is also the process that slowly destroys you. It's like burning a candle. The flame is beautiful, it produces light and warmth, but it consumes the candle as it burns. Now, I want to step back and think about what all this means, because I think it's actually quite profound, and maybe even a little bit liberating. The laws of thermodynamics are the same everywhere in the universe. Stars follow them. Galaxies follow them. Cars follow them. Your body follows them. There's nothing special about life that exempts it from physics. Let me emphasize this point because it's important. For a long time, people thought there might be something magical about life, some vital force, some élan vital that made living things different from non-living things, something that physics couldn't explain. But we know now that's not true. Living things are made of the same atoms as everything else: carbon, hydrogen, oxygen, nitrogen, a few others. The same atoms that make up rocks and air and water. There's no special life atom, no magic ingredient. What makes living things special is the arrangement, the incredible complexity and organization of how those atoms are put together, and the fact that they maintain that organization temporarily against the tide of entropy. But the arrangement doesn't violate physics. It works within physics. It uses the laws to create order locally by exporting disorder elsewhere. It's like air conditioning. Your air conditioner makes your room cooler, but it pumps heat outside. The total entropy of the system still increases, but your room gets cold. Life does the same thing with order and disorder. This is what I find beautiful about it. You are not separate from the physical universe. You're not a ghost in a machine. You're a process, an incredibly complex process of energy transformation, happening according to the same rules that govern everything else. The physicist Richard Ewald once said that the laws of physics are the same for a human being as for a stone. I think that's exactly right. But the stone is simple and static. You are complex and dynamic. Same laws, but applied to vastly different configurations of matter. Think about what this means. The atoms in your body have been around for billions of years. The hydrogen atoms were formed in the Big Bang. The heavier atoms were forged in the cores of ancient stars that exploded long before the Earth existed. You are literally made of stardust. And those atoms have been part of countless things before they became part of you. The carbon in your muscles might have once been part of a tree, or a dinosaur, or a Roman soldier, or a medieval plague victim. Atoms cycle through the biosphere constantly. Right now, you are a temporary arrangement of those ancient atoms, an arrangement that takes in energy, does remarkable things, and will eventually disperse back into the environment. Your atoms will go on to be part of other things, other plants, other animals, other people, perhaps. The show continues, even when your particular episode ends. When you feel tired, that's not a failure of your will. That's physics. Real, measurable, physical processes in your cells are functioning differently than they used to. There's no shame in it. It's as natural as water flowing downhill. And when you exercise, when you eat well, when you sleep enough, you're not fighting against physics. You're working with it. You're finding ways to optimize the thermodynamic processes in your body. You're making your power plants more efficient. You're slowing the accumulation of damage. You can't reverse the second law. You can't live forever. But you can influence the rate. You can choose, to some extent, how quickly you approach equilibrium. Now let me tell you one more thing, and then we'll wrap up. There's a deep relationship between temperature and the rate of chemical reactions. This is something called the Arrhenius equation, but you don't need to know the math. The important point is that higher temperatures mean faster reactions. Here's a rough rule of thumb that chemists use. For every 10 degrees Celsius increase in temperature, chemical reaction rates roughly double. This is called the Q10 rule. It's not exact, but it gives you an idea. Your body is warm, about 98.6 degrees Fahrenheit, 37 degrees Celsius. And this warmth speeds up all your metabolic reactions. It lets you move quickly, think quickly, do things that cold-blooded animals can't do. Think about a lizard on a cold morning. It's sluggish. It can barely move. It has to sit in the sun and warm up before it can function. That's because its chemical reactions are running too slowly. Once it warms up, it's fine, but it can't generate its own heat. You, on the other hand, are constantly generating heat. Your metabolism produces it as a byproduct, and you use that heat to maintain a constant temperature regardless of what's happening outside. This is called being warm-blooded or endothermic, but there's a cost. Faster reactions mean faster damage accumulation, faster entropy production. It's a trade-off between living fast and living long. Some researchers have noticed that animals with lower body temperatures tend to live longer. Tortoises, for example. They're cool, they move slowly, and they live for over 100 years. Hummingbirds, on the other hand, are hot little furnaces, and they live just a few years. Now you might say, wait, but hummingbirds are small. Maybe that's why they don't live long. And there's something to that. Smaller animals generally have faster metabolisms and shorter lifespans. But when you correct for body size, there's still a relationship between metabolic rate and longevity. Animals that live fast tend to die young. Here's an interesting observation. Within a species, larger individuals tend to live longer. Big dogs don't live as long as small dogs, which might seem to contradict what I just said. But actually, it's consistent. Big dogs grow faster and have higher metabolic rates relative to their size when they're young. They're burning through their thermodynamic budget faster. Warm-blooded animals like us have chosen the fast lane. We burn bright and burn out relatively quickly compared to some other creatures. That's the deal we've made. There's something called the rate of living theory, which proposes that there's a fixed amount of metabolic energy an organism can expend in its lifetime. Once you've used it up, you're done. Different species burn through this energy at different rates, which explains why small, fast-metabolizing animals have shorter lifespans. Now, this theory is too simple in its original form. It doesn't account for the fact that birds, which have very high metabolic rates, often live much longer than similarly sized mammals. There must be other factors involved. Birds seem to have better antioxidant defenses and more efficient mitochondria. But the basic insight that there's a connection between metabolic rate and longevity seems to be true. Interestingly, slight reductions in body temperature have been associated with increased longevity in laboratory animals. It's as if running the engine a little cooler reduces wear and tear. Though I should say, we don't fully understand this yet, and I'm not suggesting you go live in a refrigerator. One more fascinating fact. During sleep, your body temperature drops slightly, typically about 1 degree Fahrenheit. This might be part of why sleep is so restorative. You're temporarily cooling the engine, slowing down the damage accumulation, giving your repair systems a chance to catch up. So what does all this mean? What's the answer to the question we started with? What happens to your energy as you get older? The honest answer is that your energy processing systems gradually degrade. Your mitochondria accumulate damage. They become less efficient at converting food into ATP. More energy is lost as heat. More damaging byproducts are produced. The repair systems slow down. The vicious cycle continues. Let me be more specific about what this means in your daily life. When you're young, your mitochondria are like a fleet of brand new cars. They run smoothly, efficiently. They convert fuel to motion with minimal waste. As you age, they become like old cars with worn engines. They still run, but not as well. They burn more fuel to go the same distance. They produce more exhaust. They break down more often. This shows up in all sorts of ways you might recognize. You need more sleep to feel rested. You take longer to recover from exercise. You get tired earlier in the evening. You have less tolerance for physical stress. Your body temperature regulation might not work as well. You might feel cold more easily, or have trouble cooling down when it's hot. These aren't failures of will. They're physics. Real changes in real cells, measurable with instruments. There's nothing wrong with you. This is the universal experience of being an energy processing system in a universe governed by the second law. This is not destiny in the sense that you can't influence it. Your choices matter enormously. But it is destiny in the sense that it follows from the deepest laws of physics. The second law of thermodynamics is not going to change just because you're a living thing. Let me tell you what you can do, because understanding the mechanism points toward solutions. Exercise regularly, especially resistance training. This maintains muscle mass, stimulates mitochondrial biogenesis, and activates mitophagy. Sleep enough, 7 to 9 hours for most adults. This is when repair happens. Eat a moderate amount. Not too much, not too little. Excess calories stress your mitochondria. Eat real food, whole grains, vegetables, protein. Minimize processed garbage that creates inflammation. Manage stress. Chronic stress produces cortisol, which accelerates cellular damage. Stay socially connected. Loneliness is literally toxic to your cells. Keep learning. Mental engagement seems to protect brain mitochondria. None of this will make you immortal, but it can shift the curve. It can give you more years of vitality, more years of feeling good. The second law will win in the end. It always does, but you get to choose how you play the game. And maybe that's actually comforting, because it means you're part of the universe, not separate from it. You're a pattern in the flow of energy, a beautiful, temporary pattern. Like a wave in the ocean, or a vortex in a stream. You persist for a while, doing remarkable things, and then you dissipate back into the background. I find this view strangely peaceful. We spend so much energy fighting against reality, wishing things were different than they are, but the physics doesn't lie. The physics is honest. And when you accept what the physics tells you, you can stop fighting and start working with it. Schrödinger asked, "What is life?" And his answer, feeding on negative entropy, drinking orderliness from the environment, is a physicist's answer. It says that life is a thermodynamic process. A very special one, yes. A very complex one. But still a process governed by the same laws as everything else. You are made of the same atoms that were forged in stars billions of years ago. You are part of the same energy flow that powers the sun and moves the galaxies. The laws that govern your mitochondria are the same laws that govern black holes and nuclear reactors and everything in between. You're not separate from physics. You are physics, doing remarkable things for a while. And when that process slows down, when your power plants falter and your repair systems fail, when entropy finally wins, that's not a tragedy. Well, personally, it feels like one, of course. But physically, it's just the universe following its own rules. It's water flowing downhill, its heat dissipating into the cold. You are a flame. You burn brightly for a while, and then, eventually, the fuel runs low and the flame flickers out. That's not sad. That's just physics. And physics, if nothing else, is honest. But here's the wonderful thing about being a flame that knows it's a flame. You can appreciate the burning. You can marvel at the process. You can understand, really understand, what's happening. No other flame in the universe, as far as we know, understands itself. But you do. So my question to you is this. Knowing what you now know about the physics of your body, about entropy and free energy and mitochondria, does it change how you think about your own life? Does understanding the mechanism make the experience different? Write that down. I'd like to know what you think.